Understanding Frame Relay Part 2. I love doing accents. I just wish I was better and could do more of them. But it's funny in my kids. I have four kids, two boys, two girls. My boys immediately run and try and tackle me anytime I do that. My girls are like, Daddy, may you please not do that? It scares them. Nonetheless, here we are picking up in Frame Relay right where we left off, which is right there. We went through in the last nugget the concepts, the terminology of frame relay, and then we got into the DELSI, the addressing of frame relay. Now I want to take those and apply it to the frame relay design. Two designs that we'll look at, multi-point and point-to-point. When you are designing your network, your WAN links between your offices, you get to choose what kind of frame relay topology you're going to use, meaning what your network connections look like. You see all the dotted lines that I have through the class. It's funny how I immediately spot my errors. I've got like a stray dotted line there. But these dotted lines represent the permanent virtual circuits that are established through the service provider. Now remember, every single one of these permanent virtual circuits is a reoccurring monthly charge. Each one connects you between your offices. Each one has its own committed information rate that you can specify as how fast that circuit will go. And each one has its own set of DELSIs. So we can have addressing between the two. So I'm not even talking about the kinds of topologies yet, but looking at this, we've got Missouri, Texas, and California, and Arizona. Four locations. And we chose in this design that Missouri would be connected, this office up here, would be connected to Arizona and no other. But that means if Arizona goes down, Missouri is completely cut off. They don't have any other connections through that cloud. But on the high side, Missouri has a very low cost or relatively low cost connection compared to some of these other sites. For instance, California has two virtual circuits, one to Texas, one to Arizona. Arizona has three virtual circuits. So how you design this is really dependent on your budget. How redundant, it's a big trade-off, $ versus redundancy. So three different designs that you could really choose from. Full mesh being every site connected to every site. Partial mesh, meaning your key sites, maybe Arizona, maybe California, have multiple connections. The not so key site, all those guys do is play online games all day. So let's give them one virtual circuit to minimize the cost, because maybe if we lose that site, it's not as big of a deal. Or maybe it's not even, they play online games. Maybe if Arizona is down, that site is completely worthless anyway. There's no redundancy there at all in your server configuration. So if Arizona's down, then Missouri might as well be down too, because even if they were connected to Texas, all their resources are in Arizona. You see what I mean? So you can design it based on those kind of things. The most popular schematic for frame relay became hub and spoke. Why? It's cheapest because you have one hub sites, and that's usually how people design their server infrastructure. Is they have one hub site, maybe the corporate office, where all the servers exist, and the spoke sites just have users. Doing their job, doing their day-to-day stuff, and they all come to the hub site to get their resources. So the hub and spoke is definitely the most cost effective, but also a lot of times just in where stuff is at, it's like, well, if the hub site's down, then all the resources are gone anyway, so it doesn't make sense to have Missouri connected to Texas. Okay, one more thing. On this design, let me just clear this off. On this design, you really have to think about latency as well. Why? Because voice over IP is becoming one of those, why would you not do this kind of technologies? So not only do we have computers, but we have, for instance, phones. That we have a phone in Missouri, we've got a phone in Texas that are actually using the data network to communicate. You got your phone in Arizona that are all communicated across the data network. Now, when somebody in Missouri calls, just with the layout of this, well, let's go with it. When someone in Missouri calls Texas, they actually have to send all of that phone call to Arizona. Arizona loops around and sends it right back out over to Texas, and they communicate. Now, with Arizona and Texas, it's kind of like, okay, not that big a deal to do that sort of thing because they're close together anyway. But imagine that your hub site was maybe, let's say, I don't know, New York. Or maybe we even go national. Maybe your hub site is over in India. right? So if you had that kind of setup, if Frame Relay really did go overseas, you would actually have the phone call from Missouri go to India and then all the way back to the United States over to Texas. What do you think that's going to cost? Delay. So you've seen, television news where they have the overseas news reporter, right? And they're like, "What's it like over there, Bob?" And Bob, stands there just blankly staring at the screen, and you're like, "What do you think, Bob?" And finally, Bob is like, "Oh man, it's scary. There's bombs," and like there's this unnatural delay. You get the same thing in voice over IP, to where you're talking on the phone. You're like, "So what do you think?" Hello? And by the time you say hello, the other person is starting to respond to your "what do you think?" And they're start talking, and your hello overlaps then, and then you just get this really weird, like awkward, like, "Oh wait, okay, sorry, no, say it again," but you're still overlap. Anyway, it just makes people think something's wrong with them and they have personality challenges, but it really disrupts your communication. So what we're finding is a lot of times this hub and spoke was great for the data world because delay was not that big of a deal in the data world. Your little file transfer bar might take an extra second to get there, right? No big deal. But in the voice over IP world, we're starting to find real drawbacks to having to go through locations to get to others where it may not be optimized for voice. Not always, but it could be. This is also one of the things that as you start seeing these technologies like MPLS take hold, MPLS and these kind of any-to-any connectivity really thrives on true any-to-any. Now, again, I'm talking about the evolution. We started with X25, we went to Frame Relay, we went to ATM, and we always had this kind of concept of like, pick your connections. With MPLS, and there's a lot of ifs on this, but if you stay with the same service provider and you're using the same style of MPLS and technology, MPLS has a default everybody connected to everybody. So with MPLS, you'll find a lot of times people just paying the one monthly charge for this kind of connection, and the service provider will get you there. Now it's hard for me to talk about MPLS this way because MPLS is really just a tagging solution that service providers use. So instead of DELC numbers, they use tags, right? So that's the MPLS world. It's just service providers, since they've now started going with tags everywhere inside of their network. So let me give you a kind of, if you did have a Frame Relay connection, right? You have, we'll say, DELC 501 that gets you to Arizona. Well, as soon as you send this into a service provider that is now running MPLS at their core, what they do is they will strip that DELC off and convert it to an MPLS tag. And that allows you to route it through the network. So what MPLS, so MPLS, when I say it's a kind of packet switch technology, it kind of is, but it kind of isn't. MPLS is just kind of a universal tagging and routing system that can move packets really fast. It allows kind of a blend of everything. So for instance, you could have a Frame Relay connection coming into a service provider that converts you to MPLS at their core, and maybe they come out over here on a DSL connection. Weird, huh? To where, now over here they come out on a T1 connection, and over here they come out on I don't know, what else did I got? A Metro Ethernet. These are all different WAN connection types. So MPLS, by kind of converting the service provider to MPLS, they allow kind of an any-to-any sort of connectivity type, to where Frame Relay used to be able to only talk to other Frame Relay connections. Now it can kind of talk to everything. So when I say MPLS, everything's connected together. Take that statement at a big high level. Let me just put the capstone on that MPLS conversation by saying, you'll know when you get there. MPLS is actually not something that end customers usually run. Like, end customers run Frame Relay, right? MPLS is just kind of like, oh, by the way, that's what the service provider does. Like, that's the secret sauce of their cloud, right? That's what they're using behind the scenes to kind of neutralize all these technologies and allow this any-to-any connectivity. Okay. So let's now talk about the two different connectivity type designs that you can use for your Frame Relay network. Now I had to think for a second, because I was like, well, didn't I just talk about the designs? I did. But within those designs, you can use different methods of configuration or different methods of connectivity from those sites. Now, if we look at this design, someone tell me, what is that design? When you look at those connections, hub and spoke, right? Okay, so if that's hub and spoke, we can use a multi-point configuration. How about I use that instead of design? We can use a multi-point configuration within our hub and spoke design. We can also use a point-to-point, which we're going to talk about next. We could also use a point-to-point configuration within our hub and spoke design. It really just deals with how do we want to handle the routing, how do we want to handle our IP addressing. So let's talk about the multi-point design. So we chose hub and spoke, and you could also use a multi-point for a full mesh. You could also use a multi-point kind of for a partial mesh, and I'll explain that more when we get there. So it can apply to any of these. What a multi-point design or configuration means is that all the routers are on the same subnet. Right? So look at these IP addresses in the cloud. We've got Missouri, Texas, California, and Arizona. All of these routers are part of the 192.168.1.x. I've got a /24, so 0 subnet, and they're all kind of in this same network world. Now, I'll say the advantage of this network design is that you can save IP addresses. Right? So it's hard for me to talk about multi-point without talking about the alternative, right? So let me talk about the alternative. Let me talk about the other white meat, point-to-point, and then multi-point will start making a little more sense. If you chose a point-to-point design, what you would do is actually create a subnet for each one of these PVCs. So, /30 subnets are kind of our typical WAN subnets that we have. We could create a single /30 subnet for each one of these. So here's what that would mean. Let's say we went with 192.168.1 as our base, and we said, okay, 0 through 3/30 will be subnet number 1. Subnet number 2 will be 192.168.1.4 through 7. That'll be /30. That'll be subnet 2. Now remember, inside of there, usable, we have .1 and .2. So, this side might be 192.168.1.1. This one would be 192.168.1.2 or something. And then here we would have usable 5 through 6. So this one might be .5. Do you see what I'm doing here? .6. So what I'm showing you right there is a point-to-point design where each one of those is seen as its own little WAN link. So it's if we were to draw it kind of logically without the cloud in the middle, this is what it would look like. To where we've got Arizona connected to 3 offices. Each one of these is seen as a separate connection, and that's how it all works. Now, in my opinion, that's the better design. I like Jeremy smiles upon the point-to-point design. Why? Well, because it just makes a lot of sense. Like, this topology is normal. That's usual for us, right? We're used to okay, that's a WAN link. That's its own network, and it goes to the other side. This is not normal. It's like all these routers are part of one network, but this guy is kind of on a different world than this guy. Like it's not like I could draw it like this and say, oh yeah, these guys are all connected together like on one switch. They're all plugged in because California can't get to Missouri directly, right? It has to go through Arizona in order to get there. So multi-point design. Let me clear that off. Multi-point design says all these routers are on the same subnet. So it can save IP addresses. Why? Because every time you subnet, you have to create your own little network ID and your broadcast ID. So, for those little /30s, you lose 2 IP addresses for every single network, right? So with a multi-point design, I can say they're all one big subnet. The big problem with this is it gets confusing. Because you have to create maps. We're going to talk about frame relay maps in the next nugget. Maps that tell California, yeah, even though this guy is on your subnet, you can't really get there directly. I'm going to have to go in there and say, FYI, California, to get to Missouri, you need to go through Arizona. So I'm going to do a frame relay map. Here's the actual command. And we would say, let's say this is Delcy 601. Delcy 601 is actually used to reach Missouri because you don't have a direct link there. Okay. Multi-point makes a whole lot of sense if you have a full mesh. Where everybody truly is connected to everybody. You got something like this sideways kite going here where Texas can reach everybody directly. Then multi-point away. Do that all day. But when you start running into problems is when you have to do these weird maps to make it work, just to save IP addresses. So the big one right here that you'll want to know is that this design does cause problems with split horizon. Okay. I've got a penny here for whoever can remember what on earth is split horizon. I know you probably read that bullet beforehand, so you're already pondering it. What was split horizon? Think back to routing protocols, distance vector routing protocols. Remember the loop prevention mechanisms we talked about earlier on in the series, where we talked about infinite hop counts, for instance, for things like RIP. We talked about route poisoning that they had. Well, one of them was split horizon. And the rule of split horizon was never tell somebody about something they told you. For example, if you had two routers in the RIP world or the EIGRP world, router 1, let's just say this is the 1 network and this is the 2 network to save me the writing, right? Router 1 will say, hey, router 2, I know about the 1 network. Okay, split horizon kicks in and tells router 2, okay, router 2, never, ever, ever tell router 1 about the 1 network. Right? Because if he says, oh, I know about the 1 network too, router 1's like, well, wait a second, I know about the 1 network. You get in this little like confusing, like who's got, who's on first kind of thing. It's like who's got the 1 network, and they just keep going round and round and round and round, and they create a routing loop. So split horizon. So now let me rephrase the rule a little more technically. The actual rule of split horizon says never send a routing update out the same interface you received it on. So let me give you an example in this frame relay world. California, let's say, has the 10.1.1.0 network, right? And he tells Arizona and says, hey, Arizona, via EIGRP. Right? He says, hey, Arizona, I know about 10.1.1.0. Arizona's like, fantastic, great. I'm adding that to my routing table, and now I know how to reach the 10.1.1.0 network. But, split horizon jumps in and says, oh, you received that on serial 0/0. Never, ever, ever send it out. What's the result? Texas and Missouri never know that the 10.1.1.0 network exists, because Arizona never passes it on, and California does not have a direct connection to either one of those routers, right? So it's not able to communicate with them directly via EIGRP hello messages. It only forms the direct neighbor with Arizona. So you might say, okay, well, I see the problem. What do we do about it? Turn it off. Turn it off? Doesn't that cause routing loops? It might. It's like, well, think of all these loop prevention mechanisms that we talked about as like a 5-legged chair. How's that, right? A 5-leg chair. We just kicked out one of the legs, split horizon, to where it's like, okay, I'm still feeling pretty good. Or maybe we can rearrange, because I don't feel very good about doing that. Let's say it's a 4-leg chair where we can rearrange the legs, right? So there's a little perspective. You feel that? So I kick out this leg and kind of shift it around to where now I have a 3-legged chair where I've kind of balanced it to where those legs are pretty even, so I can sit on it. I'm like, okay, I think it's stable. I'm feeling good, but I would feel a lot better. I would feel a lot better if I knew there was 4, if I had the option of choosing. You get what I mean, right? So we just kick a leg out by turning off split horizon, and we hope that the other mechanisms that we talked about that stop the loops will step in and still prevent the loops in this scenario. I think it takes me so long to talk about multipoint because I feel like I'm presenting a technology where, at least in frame relay, there's just no case for it. Like it just causes a lot of problems. And if you have, I will say, if you have a hub and spoke or even a partial mesh design, like we saw in the previous slide a couple slides ago, I'm like, okay, it's a no-brainer. Right? Why would you not do a point-to-point topology? Just because it resolves so many issues that just happen if you use frame relay, if you use multipoint, right? Multipoint just causes issues. Let me give you a little heads up. When I went for my CCIE certification exam, this was more than 10 years ago. Wow, that's weird. But when I went for that lab exam, which is so high pressure, one of the things they force you to do in this giant day-long lab, where they just throw the kitchen sink at you to see if you can figure it out, is they force you to use a ton of multi-point topologies where it just doesn't make sense. Like this, like Cisco would be like, okay, configure that, but you must use multi-point. Why? Because Cisco wants this exam to be really hard, and they want to know if when everything starts hitting the fan and you're trying to figure out why is this thing not working, they want to be able to figure out to say, like, can you make it work? That's Cisco's question. If we throw the kitchen sink at you, if we throw multi-point at this kind of topology, can you make it work? So that's why when I'm presenting it, it's like, well, it just doesn't make sense. So this is the one that makes sense, right? Smile upon point-to-point topologies. Because point-to-point allows you, just like I showed you on the previous slide, to break each one of these into your own little point-to-point link. Now, you don't, let me share something that confused me when I first learned frame relay. I still remember it. This is how it scarred me. That I was like, okay, do I need to talk to the service provider? Do I need to tell them that I'm using a point-to-point or a multi-point? And they're like, okay, we approve your choice of point-to-point. No, we do not. All the service provider does is they deliver the layer 1 and the layer 2 connections, right? Layer 1 be physically, there's my cable in the wall, and layer 2 being like they do all this Delcy magic to make sure that when I tag something with a Delcy, it gets to the right location, right? So that's all the service provider does. Whether I use point-to-point or multi-point is totally up to me and my IP addressing design. So let's look at this. In this scenario, well, I just made it easy. I didn't even do subnetting here, right? At least nothing fancy. We took Arizona. Let's just single out this guy right here. Missouri and Arizona. Let's focus on them. Notice Missouri, 192.168.1.2. In Arizona, what I did was under serial 0/0, I did not assign any IP address. There's no configuration virtually under serial 0/0. Instead, like the router on a stick, remember that from the VLAN world? We created a sub-interface. And we said, okay, serial 0/0.100, which conveniently matches the Delcy number, 100. We'll have the IP address 192.168.1.1. So now, and by the way, there's more commands. We'll get into config in the next nugget, but I will also have to say under there, by the way, this sub-interface really does use Delcy 100. It's not magical by creating, I mean, I could create sub-interface 10,000 and still use Delcy 100. It just doesn't make sense to do that. So I still have to tell it you are using Delcy 100, and now I've got my own little point-to-point network between Arizona 192.168.1.1, okay, good, one network, and 192.168.1.2. Okay, second IP address on that same network. So then we look at each one of these, right? Each one of these. So I look at 200.2.1. I look at 300.3.1 right here. Each one of these is its own little network between Arizona and each one of these routers. Now, this is an absurd waste of IP addresses that I've done here. You would definitely want to use /30s on those WAN links to make it optimal. But by doing this, you get the point. No problems with Split Horizon. I don't have to turn it off and kick out a leg of my chair. I can still feel comfortable doing that because California talks to Arizona and says, hey, I want to tell you about my 10.1.1 network. And Arizona's like, oh, great. I received that on serial 0/0.300. That he sees as a completely different interface, right? So he's like, oh yeah, I've got no worries at all sending that same advertisement out on serial 0/0.200 and serial 0/0.100 because I see these as two completely separate interfaces. The only drawback that I could see to a point-to-point topology is it does use more IP addresses and, the configuration just looks more complex. You do a show IP interface brief, you're like, whoa, 3? But once you get used to it, I'm telling you, this is the way to go. All right. Well, I honestly really hope this concept is sort of fuzzy for you right now. Like you're looking at it, you're like, I kind of get it. I think I get it. Nope. Maybe, well, that's the kind of feeling because it makes me feel better because it took me so long to get frame relay when I was first learning it back in the day. And I'll tell you what did it for me was seeing the configuration and not just the configuration of these guys, like the routers, connecting to the cloud, like, okay, they're going in, they put their Delcy. Like I saw that and I'm like, it still feels fuzzy to me. What it really took, where the light bulb went off for me is when I saw the big router in the cloud. Like once I finally saw the service provider configuration, and I'm like, oh, that's okay. That's all they're doing. That's where the light bulb. I was like, aha, that makes sense, and that's where it came together. So in the configuration nugget next, I'm going to show you the config of point-to-point, of multi-point, but I'm also even going to dig into the cloud a little bit and show you what the service provider's doing. For now, I hope this has been informative for you, and I'd like to thank you for viewing.